Hello, everyone. Now that we're at the top of the hour, I want to thank all the audience for being here, as well as our very distinguished presenters. This is an exciting event. This is the first event of this type that we've done for quite some time, and so we're hoping to make this part of a series. So thanks, everyone, for joining us for the inaugural one in this series. We'll hear about some very exciting research that people are doing, and we're going to get our event started off with a quick presentation by Oliver Ruebenkoenig, who's going to talk about PDE models in the Wolfram language, as well as introducing some new features that have just come out. And then we'll get into a sequence of presentations, which are coming from research experts from around the world on a variety of methods and applications for working with partial differential equations, solving them numerically, and their applications. Without further ado, I'll stop sharing my screen and hand things over to Oliver Ruebenkoenig.
All right, so I work in the numerics group at Wolfram Research, and I'm going to give a small overview today of what we've done for version 14 and show a specific application example that I hope is of interest to a few people. Okay, so version 14, currently we're working mainly on PDE models, basically to provide functionality that makes it easy for you to set up partial differential equation models. We have a set of domains, like domain fields of physics that we have, where we provide these functions for. And so we had acoustic for a while, mass transport. In version 14, we've updated the heat transfer, we've updated solid mechanics, there's new domain, electromagnetics, fluid dynamics is new, and we also have a Schrödinger operator now. So I'm going to show a few of those in the next few slides. So if you've never seen these PDE operators, here's an example. So a heat transfer PD component. This is how you'd specify one of these things. So you specify T as a temperature of spatial variable X, another X here. There's no options here. And that's going to give you a heat equation, or part of a heat equation, a PDE component, so to speak. Here's a time-dependent version. We've just added the T here. So now we have a time-dependent version, and you see the first order time derivative that appears now. You can specify properties of this, like a mass density, specific heat capacity, and it's going to fill out things as it's supposed to do. You can also use things like material, copper, and it fills in the exact material parameters for these specific materials. Now, one question is, why would we want to do that? So while for the heat transfer, you might be able to write this down manually, things become much more complicated when you, for example, look at solid mechanics. So here we have a Neo-Hooken material law, a shear modulus, a thickness, and this equation actually, it becomes a little more involved. So that's not something you'd write off down top of your head. So that's why we provide these PDE operators. Okay, so let's have a look at what we've updated so far. So for heat transfer, maybe I'll show you one thing first. So because these monographs that we provide to supplement the functionality become larger and larger, it's sometimes hard to find what has changed. So if you look at the documentation center, you see this is the monograph for heat transfer, and you see here the updated show changes, hide changes, and if you then activate that and scroll down through the document, you actually see some, you should see some right here. So for example, here's a spot in yellow. Those are changes that we've added new, and there's entire new sections here that's new. So that's how you can keep track of the changes that we've made in the documentation. So we've reworked the heat sources a bit for volume point and line heat sources. We added new examples, temperature dependent heat capacity. All of these are links. So if you're interested in any of them, you can click on them and they'll lead you directly to the documentation where you can have another look. Okay, so there's also updates in solid mechanics. So we've added axis symmetric solid mechanics models. We've added new material models, transversely isotropic materials for linear elastic materials, non-orthogonal material orientation. That's interesting if you want to do things like materials that are in layers, for example, or materials that are not oriented. The transversely isotropic material model is for things that are in layers, and the non-orthogonal material orientation is when you have material that is non-axis aligned. Then you can use this technique to make it axis aligned and simplify your life a bit. We've made quite a few updates to the hyperelastic material models. So we've added Mooney-Rivlin models, 2, 5, and 9 parameters. Neo-Hooken is now available in compressible and in nearly incompressible versions. Ayuda-Boyce, Ghent. The point is, even if your favorite hyperelastic material model is not available, all of these material models that are available are actually visible to you. So you can look at the code and use those as a basis to extend the system with your own hyperelastic material laws if you're so inclined. So nearly incompressible material models have been added. We've added an entire section on model calibration. That's something we're really proud of because it's very easy to do in Mathematica. You just use a function like findFit. It spits out the fit parameters, and you can directly feed them into the nonlinear model. So that's very easy here. We've added plane strain, plane stress models for the hyperelastic materials, multi-material models. So if you have several materials, physics coupling, I'm going to show an example of that. And also transversely isotropic material, standard reinforcing material. So the list is quite long. And I'm going to show a few quick examples here. So here's an example where we have a material that's reinforced with fibers. So in the background, you see a slight gray box. So, and you imagine that there's fibers in this direction running. And if we pull to the right, that's the deformation you will get of this object. Now, if I change the orientation of the fibers, now you see them a bit better there in the background, then the deformation of the object starts to change as well. So if we go a bit further, yet a bit further. So this is 45 degrees. So that's how this material would deform if you pull to the right, but you have a fiber reinforcement in that material. Here's another example from the hyperelasticity, and that's basically showcasing our capabilities to couple hyperelastic materials with several fields of physics, like in this case with moisture. So it's a mass transport and a temperature type of thing. And let me quickly start the video here. So what you're seeing here is a gasket that's made of a hyperelastic material, and it's coupled to moisture and temperature PDEs so that we can show the deformation and how the moisture is entering this gasket. So again, this is an application example from the documentation, and you can find the details there if you're interested. A next new topic where we've started afresh, basically. So this is the first addition in a series of electromagnetics. We started with electrostatics. There is an entire monograph accompanying this functionality. We have PD components and boundary conditions. So the PD component is the electrostatic PD component. We have a potential condition, electric flux density, and symmetry value. All of those are in the documentation, of course. And that's a first step into a larger area. So you can expect to see more of this electromagnetic functionality in future releases. I'll get to that in a bit. One function I'd like to show that's maybe that I don't want to go unnoted, so to speak, is a new function. It's in the finite element context, and it's called discontinuous interpolating function. So interpolating functions have problems when the function that they're interpolating is discontinuous, or when the derivative of the function is discontinuous. And that's something we'd like to address with the discontinuous interpolating function. So let me show you an example. So this is a finite element mesh with two material regions. We have this dark gray region and this light region, and we have a function, and we say if the element marker is 1, so if it's in one of these regions, then the value should be 0, and if it's in the other region, the value should be 1. So if I call this evaluate on element mesh, and now I've added this option, discontinuous interpolation goes to false, to give us the legacy version. So this is something you'd get in version 13.3. You get a normal interpolating function. And if I look at the maximum and the minimum values of this interpolating function, we'll see we have a little bit of an under and an overshoot. And this is what you also see in this image here. So when we interpolate this, we have this under and overshoot. And to the problem, we get to the problem in a bit. But now in this new version, if you call evaluate an element mesh with this function, you get a discontinuous interpolating function. The min-max values are 0 and 1, as one would expect, and the plot is now nice and crisp. So this is a new addition. Right, so if we look at a cross-section through this plot, and we specifically look at this point on the interface. So if I evaluate at exactly this point here, I'll get a function value of 1. But so it belongs to this type of area here. So, but we might want to add this point to this area here. So that can also be done. But let me show you first what the problem is. So if I have a function point that's exactly on the interface here, we can't really decide whether it goes here or here automatically. That's some information that we'd need to know. And that's basically also the flaw of the interpolating functions. When they evaluate a function here on that interface, they don't really know where this point should belong to, and it's kind of random what they do. And that's why you saw these over and undershoots in this first plot. So what we've added is a new new option, called marker priority. There you can specify which of the regions should have precedence, and then this point gets attributed to that specific region. So again, this is the function 0 and 1. We have the marker union, so 0 and 1 are the markers that are present in this mesh. And this is what we saw previously. If I evaluate this function here, I get 1. Now, if I call evaluate an element mesh again, and now I set the marker priority to 1, 0. So that's just the reverse of this. I want to prioritize the markers differently, and I evaluate at the interface point. Now this point here is attributed to the other region. Okay, so here's an example where this comes up. This is an electromagnetic example. So we have a copper and an iron multi-material model, a potential on the left and the potential and a ground on the right. And this is the accompanying mesh. So what we do now is we set up the variables, the potential in x and y, independent variables, electroconductivity is a piecewise function. So in one region we have this value, and in the other region we have that value. We call ndsolve, and we get an interpolating function. And now when we visualize this function, we see that this function is like z0 continuous. So we have a discontinuity here. Right. What we can do now is we can go ahead and use the discontinuous interpolating function and feed it the interpolating function that ndsolve returned us. And it's going to transform this into a discontinuous interpolating function. This gives you the bounds of the function. And here at the back, we see the marker priority 1, 2, again. So you can call the gradient on that. It's going to work exactly like an interpolating function. And now if I evaluate that, I get a specific value at that point. And if I change the marker priority, I get the point that belongs to the other region. So that's the one thing I wanted to also show a bit, because I think it's useful functionality if you run multi-material models and have a discontinuity. Now, we also added new functionality in fluid mechanics, so computational fluid dynamics. There is a monograph. The PD component is called fluid flow PD component. It's capable of solving compressible, incompressible Navier-Stokes equation, non-Newtonian flow with non-Newtonian material models. And again, all these material models are available for you to see and look at the code of how we've implemented them, so that you can write your own if your favorite model is not present. There's also the possibility to do multiphysics with the fluid flow module, of course, through the Boussinesq approximation. So they can couple a heat transfer equation to it. It's all, yeah, that's there. A lot of our customers are actually physicists, so we thought it might be good to have some functionality that's specifically geared towards those people. And we've added a Schrödinger PD component. There's a very nice blog post that came out, I think, yesterday or the day before that, that shows nice application examples of the Schrödinger equation. But again, also in the documentation, you'll find a lot of material of how to use this specific component. One other thing I'd like to draw your attention to, we started to make a collection of PD models best practices. So if we go to help system again, this is a collection of things that come up often with generating PD models. So you can have a look here, exploiting symmetries of geometries, how to model Dirac delta functions, how to deal with infinite domains. So they're not specific for a particular application, but they are things that come up generally. So that's another piece of information that might be useful for you. Okay, then I think, right, there's one, right, that's one thing I wanted to talk about. So what is the future going to hold? So as far as I can see, so we're going to have electrical currents in the next version. So extending in the electromagnetic area. Possibly we can add magnetostatics. Not quite sure yet if that's going to make the next release, but if not, then it's going to be the release after that. We're also working on electromagnetic fields. That means the full Maxwell's equations. That's certainly not going to be in the next version, but hopefully coming up soon. For solid mechanics, we're working on plastic deformation. Yeah, we'll see how far we get, whether it's going to make it into 14.1 or maybe 14.2 or whatever the next versions are going to be called. If you have specific requests or specific areas that we should look at, please contact me. I always like to chat with customers, and I can see. I'll try to see what we can make happen so that something like this can go off the ground. Yeah. Right, summary, undissolved rocks. As a developer in the numerics group, I must say it's my favorite function. I hope you enjoyed this small presentation, and that's where I'm going to halt. And I think we have some time for questions and answers. Okay, so anything for piezoelectricity or laminated elastic structures. So laminated elastic structures, so that means multi-layers, not that I can think of right now, but maybe that's something we should put on the schedule, on our agenda to do. So maybe you want to contact me and send me an email, and then we can discuss a bit what you specifically look at, and then we can see maybe if you can get that off the ground. Next questions. Wind tunnel functions. By wind tunnel functions, I assume you mean turbulence modeling. I started looking at turbulence modeling, but it's complicated and I didn't want to make any promises for how long it's going to take me to do, but it's on the agenda. But don't hold your breath with it for the next version yet. So I don't think it's going to make it to the next version. Are you generalizing the available boundary conditions? Generalizing the available boundary conditions. If you let me know how you'd like to generalize them, let me know and I can have a look if I can do that.
Hello, colleagues. My name is Oleksii Semenov. I'm from Ukraine. I work in Photon Electric Welding Institute, and my presentation is devoted to mathematical modeling of whirlpool formation in tungsten inner gas welding. And here are the concise structure of my presentation. First of all, I would like to speak about the motivation, and then I will speak about the main driving forces which acts on the molten metal in the whirlpool. And then I will describe the mathematical model which we use to simulate the whirlpool formation, and then I will show you some numerical results obtained by this model. And after I made some conclusions. And on this slide, here are the schematic of tungsten inner gas welding. Tungsten inner gas welding is a very popular welding procedure in the manufacture. The arc burns between the non-consumable cathode. It is usually made of tungsten and the base material, and whirlpool forms. And it is very important from the technological point of view to control the well penetration. And there are some technological tricks to influence upon the well penetration. And the very new approach is the so-called high-frequency pulsed current welding. The welding current is changes by means of square wave pulse. It is very difficult to realize this pulse technologically, but it is simpler to simulate the influence of such modulation on a weld pool. And wait a little bit. On this slide, you can see the main forces which act on the molten pool. The heat transfer in the melt pool by two mechanisms, the conduction and convection, but convection dominates. There are several forces which drive the molten metal in the pool. The first one is the buoyancy, and the second one is the Lorentz force. The Lorentz force appears due to the interaction of welding current with self-magnetic field. And the Lorentz force initiates the so-called electrovertical flow in the well pool. There is also two surface forces. The first one is the Marangoni force. The Marangoni force appears due to the difference of the surface tension on the well pool surface, and surface tension of the metal depends on temperature and concentration. Several impurities influences upon the surface tension, and also there is also another surface force which is the plasma shear stress. This force appears due to the mechanical interaction of the arc plasma and the fluid inside the melt pool. And in our model, we made several assumptions. First of all, we suppose that all the physical processes inside the melt pool are axial symmetry. This assumption simplifies significantly our approach. So we assume that welding process is that the heat source is at rest. And the second assumption is pre-surface about pre-surface. We suppose that pre-surface is flat, so the computational domain is not changed. And the last assumption about the current density on the anode surface and heat flux into the anode. We use the previously obtained results by means of arc model to set the boundary condition on the anode surface. And our mathematical model is self-consistent model. It consists of heat transfer, hydrodynamics, and electromagnetic models. The first sub-model is heat transfer model. The heat, as I said, is transferred in melt pool by convection and conduction, and convection dominates. So the energy conservation equation takes into account both convection and conduction. We also take into account the latent heat of fusion, and we use the heat transfer equation in enthalpy statement, and the next boundary condition we set on the free surface. As I said earlier, we use the heat flux from the plasma obtained by means of the ARC model. And here are the model of electromagnetic processes. This model is based on the so-called magnetic diffusion equation. This equation is a part of magneto-hydrodynamics approximation. We take into account the eddy currents, but displacement currents are beyond of this model, so we don't pay attention on electromagnetic waves. So to set the boundary condition, we need to know the current density distribution on the anode surface, and this distribution is obtained by ARC model. And to calculate the current density field, we use the Ampere-Maxwell law. So if we know the current density field, we can obtain the Lorentz force, which acts and rotates the molten metal in the whirlpool. And the last submodel, and maybe the difficult model, it is a hydrodynamic model of hydrodynamic processes. This model is based on the incompressible Navier-Stokes equation in Boussinesq approximation, and we suppose that the free surface is flat, so we can use the next boundary condition. The normal velocity on the free surface is 0, and also the Marangoni effect and plasma shear stresses are taken into account in the balance of tangential forces on the tangential stresses on the free surface. And the body forces contain the Lorentz force, the buoyancy, and also the so-called Darcy-like force. We solve Navier-Stokes equation both in solid and liquid domains. Both in solid and liquid domains, and to suppress the fluid motion in the solid domain, we use the so-called enthalpy porosity model. This is a very often used model to simulate fluid flow coupled with phase change. And for temporal discretization of advection terms, we use so-called characteristic base scheme. It is well-known method for discretization of convection-dominated problems. This method is well described by Zienkiewicz in this work, and the main idea is discretization of the total Lagrangian derivative along the characteristic or the fluid particle trajectory. For discretization in space, we use the finite element method, Galerkin finite element method, and for the next shape functions for temperature and velocity are used. This is so-called Q2, Q1 element. This element satisfied the Ladyshinska-Babushka-Brezzi condition. And pay attention, please, that the finite element mesh is very fine near the surface because due to the Marangoni force, there are large gradients of the velocity appears. So we need very small elements in this region. And this algorithm was realized in Wolfram language, and this is so-called self-written or in-house code. I did not use the built-in function, so it was attempt to realize the solution algorithm at a low level. Let I show you some numerical results. On these slides, you can see the technological parameters of TIG welding, which we used to simulate. We consider the argon welding with the next parameter, the welding current, the square wave pulse were used for welding current description. And also we considered for comparison purpose the welding with direct current welding, direct current, and which equals to mean value of the square wave pulse. Here are the properties of the steel. We consider the welding of the steel, and pay attention please that the temperature dependence of surface tension is non-monotonic. And this feature will lead to some interesting results. Here are the results obtained by arc plasma. These results we used to set the boundary condition on the free surface, the current density, time-varied current density on the free surface, heat flux from the arc into the anode for two modes, direct current and high-frequency pulse current, and also the plasma shear stresses on the anode. And here are the results of simulation of whirlpool formation for direct current mode with welding current equal to 140 amperes. Pay attention that the flow pattern in the whirlpool consists of three cells. There are two subsurface flow and they appear due to the Marangoni force, and there is also a flow pattern, and this flow pattern in the deep can be ascribed by the influence of the Lorentz force. And here are the temperature distribution on the anode surface and along the axis of the whirlpool. It is interesting to note that the velocity on the free surface is very high. It exceeds 1 meter per second. And pay attention on the figure on the bottom. Here are the comparison of the Marangoni shear stress and the plasma shear stress. And we see that the Marangoni, the sign of the Marangoni shear stress changes. And we also carried out the comparative analysis of direct current and high-frequency pulse current modes. And you can see the comparison. The time is counted from the beginning of the process start, and we see that in the high-frequency pulse current mode, the penetration is bigger. This is due to the difference in Lorentz forces in direct current and high-frequency pulse current. Unfortunately, we did not take into account the free surface deformation. It is very challenging task. But in high-frequency pulse current, the arc pressure on the anode surface is much bigger in comparison with direct current. So in real experiments, the difference usually is bigger. And here you can see the flow structure in the weld pool. In high-frequency pulse current welding, we also obtain the three flow cells. And I want to mention that on the free surface there exists so-called stagnation point with zero velocity, and this is due to non-monotonic temperature dependence of the surface tension. So the next conclusion, I would like to say the Mathematica offers a wide range of possibilities for the development of the self-written or in-house finite element code. The model describing the physical processes in the weld pool during thick welding was generalized to high-frequency pulse current modulation. The numerical algorithm based on finite element method was realized in Wolfram Language. We have carried out the comparative analysis of penetration in argon, direct current, and high-frequency Pascal and thick welding of this steel, and we developed the in-house code. This in-house code can be used not only for welding simulation, but for simulation two-dimensional plane or axisymmetric magneto-hydrodynamics incompressible flow coupled with heat transfer and solidification and melting phenomena. And in future, we plan to take into account the free surface deformation, and it will be the subject of our future studies. I would like to acknowledge, I would like to express my thanks to Henrique from University of Georgia for his excellent answer of my question on Mathematica Stack Exchange and for sharing his sparse matrix assembly routine on Mathematica Stack Exchange. And also thanks a lot Oliver from Wolfram Research for his continuous support. And also I would like to thank to Wolfram Research for providing a free 1-year license of Mathematica to National Academy of Science of Ukraine. It is a very big support. Thank you a lot. Thank you for your attention.
Thank you. So the title is slightly different, but it is still a related title. And my name is Yury Vetyukov. I'm doing research in the field of solid mechanics in Vienna, Austria, and we have seen that NDSolve can do a lot in the field of solid mechanics out of the box, but not everything. and I will try to demonstrate that even if ND-solve functionality is not that advanced to solve your problem immediately, so that it is not at your fingertips, but still you can use Wolfram Mathematica to develop your own simulation routines very efficiently. So the first example will be bending of elastic plates. This is a square plate, some very simple academic example, clamped at all four edges under the action of the distributed force P. This can be a weight of this plate, the field of gravity. So green lines seem to depict the deformation, the bending of this plate, and the deflection W should follow this partial differential equation. So P is the lowering, this is the Laplace operator, and D is the bending stiffness of this plate. In Cartesian coordinates, this partial differential equations has a form like this. So D is a reserved symbol, that's why I'm using DD for the bending stiffness here, and partial differential equations of the fourth order, to my knowledge, cannot be solved by ND-solve right now. And we need to solve this differential equation with account for the boundary conditions, so there are no deflections at the four edges, and some slopes should vanish because of the clamping condition. That means these directional derivatives of the deflection should also vanish there. And this strong form of the boundary value problem is difficult to solve. That's why we frequently prefer in mechanics to use the equivalent weak form or the variational equation. That means that the deflection field W, which exactly fulfills this boundary value problem, would at the same time deliver a minimum to the total mechanical energy of our system in the state of equilibrium. And this total mechanical energy comprises the potential of the external force, capital W. This is an integral like this over the domain A. And the strain energy is the integral of the strain energy density, which is a quadratic form of the curvature kappa. And nu is another material parameter, Poisson ratio. And this curvature kappa is a tensor. That is the second order gradient of the deflection. And in our Cartesian coordinates, it is evaluating to this matrix of components. And the advantage of this weak formulation is that we can use the Ritz approach, so that we do minimize the energy, not for all functions which can be imagined, but rather for the linear combinations of some shape functions times the degrees of freedom Q. And the better the choice of the shape functions, the more terms do we take, the more accurate the solution is going to be. And when we plug this approximation into the energy expressions, then we obtain for the strain energy this quadratic form. K is the stiffness matrix, the potential energy is the linear form, F is the force vector, and then we seek the minimum. We set this partial derivative equal to 0. This results into the linear system of equations. We solve it, plug it into the approximation, and obtain the approximate solution. So let's see how it works. First, on the very simple example of a single term Ritz approximation. So our W, our deflection, is Q, the unknown degree of freedom, times this shape function. And this shape function is visualized here. It fulfills all the boundary conditions, and it corresponds to our expectations how such a plate would bend. And just the scaling factor Q is to be found out so that the total energy would be at minimum for this sort of deflection fields. We compute the curvature, we compute the strain energy density, we integrate the strain energy density over the entire domain and obtain this quadratic form. This is similar to a spring. You know that the energy of a spring, the potential energy of a spring, is quadratic in its deflection. And this is the potential of the distributed force. We assume P to be constant, like weight of the plate, and then we minimize the energy. This is the total mechanical energy. We compute the derivative with respect to the degree of freedom, set it equal to 0, solve the equation, and find this value of the degree of freedom. We plug it into our approximation and evaluate the deflection at the center point of our plate, where x and y are 0. So this is the deflection of the plate in our solution. And the exact solution is known from the literature. We can make a relative, we can compute the relative difference and see that the relative difference is approximately 5%. Not bad for such a very simple approach, just a single term Ritz approximation, but sometimes we would like to have better accuracy, sometimes we would like to treat some asymmetric loading conditions, sometimes we would like to treat some different boundary conditions where this very simple approximation would not be applicable. That's why we need something better, something more advanced, and I will present you some bicubic finite element model, which guarantees C1 continuity across the finite element edges. This is very relevant for these structural mechanics sort of problems, because if we would have a kink between the finite elements, this kink would mean infinite curvature, and infinite curvature makes troubles. That's why we need to develop such an approximation which preserves not only the continuity of the deflections, but rather the smoothness of this deflection field. And the basic ideas of this finite element could be found, for example, in this paper. And here you have you can imagine how this element is constructed. This is a square element embedded into the xy domain. Xi and eta are the local coordinates of this finite element. In each of the 4 nodes, we have 4 degrees of freedom, namely the deflection, 2 slopes. These are the directional derivatives with respect to the local coordinates, and 1 mixed second-order derivative. And with this 16 degrees of freedom in total, 4 in each node, there are 4 nodes here, we construct the approximation of the deflection field on a finite element using these shape functions S in this sum here. And here are the appropriate shape functions. These are the algebraic expressions, and these are the graphical presentations of these shape functions. So this one is responsible for the deflection in the first node. This one is responsible for the first slope in the first node in the direction of the xi coordinate. This is the second slope in the eta direction. And this one is responsible for the mixed second-order derivative. And these are for the rest of the nodes. So this function determines the degrees of freedom of a single node, deflection, one slope, another slope, second-order derivative, and then we make a linear combination of the shape functions with these coordinates in all the nodes, and this is the approximation of the deflection field on a single finite element. Now we can imagine a block of finite elements, and let us evaluate the deflection fields on all the 4 finite elements for some exemplary values of the node degrees of freedom. Here you can see that indeed the deformed shape of the plate on this block of 4 finite elements is C1 continuous. It is smooth across the finite element edges. And if we change the slope in the middle node, then we see that still the continuity condition is fulfilled, but the deformed shape is, of course, changing. Now that we have the deformation, we can compute the energies. For this sake, we use Gaussian quadrature rule, which is conventional in the finite element analysis. So here I have programmed some integration routine for which uses this grid of 3 × 3 Gaussian integration points, and then we integrate the potential of the external forces. We integrate the strain energy over the finite element. For this sake, we compute the curvature, and it features the second-order derivatives with respect to xi and eta, and they are recomputed into the second-order derivatives with respect to the Cartesian coordinates x and y by this vector in front of the term. And this is the quadratic form of the strain energy of the single plate finite element. And then we assemble the entire model. We use 4 × 4 finite element mesh. These are the physical parameters of our problem: some dimensions, bending stiffness, Young's modulus, thickness, and the plate is deforming under its own weight. And we need to establish a relation between the local node numbering, which is depicted here by red numbers, and the global node numbering, which is depicted here by green numbers. So this one node in the global numbering has different local node numbers depending on the perspective, depending on the element from the perspective of which we are looking in this node. So it can be the node number 1, number 2, or number 3, or number 4 for all these 4 finite elements. But still it is the same node. So these 4 finite elements share the degrees of freedom of this node. And then using this substitution, we sequentially evaluate the energies for all the finite elements in the global node numbering. We sum up to obtain the total energies. And the next step would be to determine the degrees of freedom with respect to which we would like to minimize these total energies. So these are all the degrees of freedom of the 25 nodes, 5 × 5. This makes 100 degrees of freedom, but many of them need to be constrained because of the boundary conditions. So these are the ones which need to be constrained because of the vanishing deflections and slopes at the edges, and there remain only 36 degrees of freedom These are the active degrees of freedom. And then we extract the stiffness matrix out of the quadratic form of the total strain energy. The stiffness matrix has a sparse structure because of the mesh topology, not all degrees of freedom are coupled with each other. This is the force vector. Many entries in the force vector are just round of errors. They should vanish in the exact formulation, and they should vanish because of the symmetry of our problem. And then we solve the system of linear equations, obtain the degrees of freedom, and evaluate the deflection in the middle point, which is now very close to the theoretical value. You see that the difference is minimal. We can also plot the deformed shape. It corresponds to our expectations, how such a plate should bend under the direction of its own weight. We can also change the lowering, for example, from the distributed one to a concentrated force acting in the middle. And if we set this concentrated force equal to the entire weight of the plate, so that we concentrate the entire weight of the plate in the middle point, then we just need to recompute the potential of the external forces. This is the new force vector with just a single entry, because the entire force is acting on just a single degree of freedom in our model. Then we again solve the linear system of equations and obtain some very larger deflection field in our model. What else can we do? We can do some dynamic analysis. We can do some natural frequency analysis in our model. So now we treat some transient process. The deflection is now a function of two spatial coordinates and one time variable. So the partial differential equations would feature derivatives with respect to all these three variables. But in the Ritz approximation, the things are very much simpler. We compute the velocity of each particle in the transverse direction. We compute the kinetic energy, which is now the quadratic form, and M is the mass matrix. And in the discretized model, we have this system of ordinary differential equations with the mass matrix and stiffness matrix, which describes the free vibrations of such a plate. And these free vibrations would become a linear combination of single vibration modes. Each of them is a harmonic process in time with the natural frequency omega k. And for the natural frequencies, we have this generalized eigenvalue problem. So the stiffness matrix is at our disposal. We just need to compute the mass matrix. For this sake, we compute the potential, the kinetic energy of a single finite element. We assemble the kinetic energy of the entire finite element model. We obtain the mass matrix. Then we solve the generalized eigenvalue problem and find the 6 lowest eigenfrequencies, natural frequencies of this plate. So this is the smallest frequency. The second frequency and the third one are identical because of the symmetry of the problem. And these are the 4th, 5th, and 6th eigenfrequency. And we can also plot the respective vibration modes. So this is the deepest frequency vibration mode. These two are symmetric ones. And these are the higher vibration modes. And in this context, it is very interesting to check some historical remark. There was a German physicist, Ernst Chladni, who was traveling across Europe some 200 years ago, presenting some very simple mechanical experiment. He would take a plate, a flexible plate, and would excite vibrations by using the violin bow on the edge of such a plate, and he would scatter sand on the surface of this plate. And the sand would form some very interesting patterns depending on the vibration frequency. And these patterns are the lines, the nodal lines of the respective vibration modes at which the respective amplitudes are vanishing, so that we have now a possibility to numerically reconstruct these Chladni figures, which he presented even in the imperial courts in Europe, and Napoleon was very much excited in these findings. And I'm seeing that my time is running out slowly but steadily. That's why I will be presenting the second example very briefly. So here we deal the vibrations and large vibrations, which makes the problem nonlinear, of a cantilever beam. The position vector x is parameterized by this arc length coordinate and time tau. And these are the equations of the beam theory written for the nonlinear case. You can see that they form some pretty complicated system of nonlinear partial differential equations. And instead of solving these equations in the strong form, we prefer solving the weak form, so that we discretize this beam into several finite elements. Each of them is bounded by 2 nodes. And these are the shape functions for the discretizing both components of the position vector, so that here you see these x and y are the unknown scalar functions. And in each node, we have 4 degrees of freedom. These are the values of the x and y coordinates, and these are the slopes, the local derivatives of both coordinates with respect to the arc length coordinate on this road. Then we approximate the position vector on a single finite element. We compute the strains. We compute the axial strain. Although we assume the rod to be inextensible, we still cannot guarantee the vanishing axial strain with this kind of approximation, but we can penalize this axial strain by using some very high tension stiffness. Then we compute the curvature, and this curvature is the bending strain. It determines the bending strain energy of our rod, which is very relevant for us. We constrain some of the degrees of freedom of the leftmost node because of the clamping condition. Then we choose the number of finite elements. We use 8 finite elements, which provide us with a very accurate solution. And the total potential energy is just the strain energy in the free vibration process. And this is the integral of the bending strain energy. A is the bending stiffness. Kappa square is so A times kappa square over 2 is the corresponding distributed bending strain energy. And this is the penalty term which should make the rod inextensible. So B is the very high tension stiffness. Then we compute the strain energy of a single element by using the Gaussian quadrature rule. We integrate the total strain energy, we integrate the total kinetic energy, we integrate the total potential in the field of gravity. These are the degrees of freedom of our model. And then using the mechanical principles, we assemble the equations of motion of the discretized system. These are the ordinary differential equations for all 33 degrees of freedom. Then we choose some set of physical parameters. We solve first the statical problem by minimizing the total potential energy of our system. This is the static deflection of our beam. And in the next step, we proceed to the time integration. We integrate the equations of motion over 3 seconds. And the first attempt to use ND-solve fails because of some error message. And I'm hoping to discuss with Oliver Ruebenkoenig at one day why this happens. It didn't happen with Wolfram Mathematica some many years ago, but now it is unable to solve this sort of differential equations of ordinary differential equations from the very beginning. But instead of that, it suggests to use this option, which effectively transforms the solver to the differential equation, to differential algebraic equation solver, which is less efficient, but it works. Okay, we use this workaround. We run the time integration, which takes about half a minute, and it generates a huge amount of data, but now we can post-process the solution. So this is the time history of the deflection of the vertical coordinate of the tip of the rod. So you can see deepest that the lowest natural frequency is dominating in our solution. And here you can hopefully see the animation of the vibration beam on your screens. So it looks natural, and I'm hoping to have given you an impression that pretty complicated sort of problems can be still solved in Wolfram Mathematica very, very efficiently. And yes, my time is over. I thank you for your attention. And if you have questions, please free to ask me. This notebook should be available to you in the handout materials, and you can also contact me per email if you're interested. Thank you.
Excellent. Thank you, everybody. Thank you, the organizers, and also all the great people who have worked together with me on this project that I happen to both lead and represent at the Naval Research Laboratory in Washington, D.C., on a project that has been evolving since perhaps Mathematica was in version 0.99, but has dramatically accelerated in the last 4 years by funding from DARPA. So I'm going to jump in directly on the motivation. At the Naval Research Laboratory, since we are related to the Navy, we have many applications that involve multiphysics. And here on the left, you see the case of an electromagnetic launcher, what is colloquially called a railgun, where you have a projectile that is being propelled by the Lorentz force that is being developed due to the fact that it has to be normal to the cross product of the magnetic field and the electric current density that is passing through the rails. One domain is stationary, the rails, and the other one is moving. And we've been asked to model really how this system degrades, because it's very essential to be able to use it multiple times before actually it damages itself from multiple use. Now, the physics that are being involved on this project are involved just about everything that is out there, including all the electromagnetics, so Maxwell-Ampere law and the Gauss law, written in terms of the vector and scalar potentials, are the equivalent form of the Maxwell equations. Then we have the energy conservation equation, that is an evolved form of the heat conduction equation. We have a conservation of momentum equation that deals with the structural equilibrium, and we have a number of reactive mass conservation PDEs that deal with a reacting species when everything is molten in the interface of these two bodies. And not only you have to solve these equations, but you actually have to solve them twice, one in the macro scale and one in the mesoscale. So we're dealing with a strongly coupled system where you can see the state variables participating on the right-hand side of these equations, which is completely cross-coupled. We have 6 generalized PDEs plus R PDEs, depending on how many species we want to include in the physics. Well, we solved this problem, but what did we learn? And this is what I wanted to focus. You know, in every opportunity that you have to solve systems of PDEs, you really have, by using resources, FEA, finite element resources, you have a pre-processing stage, a processing stage, and post-processing stage. And if you really look at the role of the computer, where the icons are, and the role of the people, and then you measure the time that you spend into performing each one of these operations, you find out that out of the entire problem, only 1% of the CPU of the time is the CPU processing, the one that the problem is being solved. Remember, this is a problem that sometimes can reach 2 to 3 billion degrees of freedoms with a B. So you need to address all the issues that till you get to the final solution that involve the fine-tuning of the model and the solver and everything that is being involved in the selection of the convergence criteria and the pre-processors and the post-processors, the preconditioners and the post-conditioners and all of these things. So this donut here shows you really that most of the time goes in fine-tuning, and some of the time goes in the pre-processing for developing the meshes and everything that you need. And 16% of the time goes in the post-processing, which is evaluating the results. So clearly that shows that we have a very ominous role for the user in this place, and this process is not nearly efficient. So we actually looked in the context space of where really a model lies and what kind of decisions the users have to take. So if you consider a model to have an analytical form in the physics model representation and a computational form where it can be split into a numerical model, into a software model for this numerics, and a hardware model, bringing in the hardware you have to deal with, and you look carefully at the basis of this context space, you realize that you end up very quickly with 35 plus bases that show you areas that the user has to make a decision, and usually the user has to evolve in that space until it gets to the place that it gets the proper results. And it's not only the number of the domains, the number of the fields, the number of the scales, it's a whole bunch of other things that are associated with the analytical model. There is the numerical model approaches that you can follow. There is, again, the software conditions that you have to select. And again, as I said, the hardware one that's split also involve the networking capabilities and the time capabilities that actually one has at his or her disposal. So what are the issues really? we already said the user role is extremely costly and inefficient. So we have an opportunity to improve this and try to get the user out of the loop. We have an incredible complexity that is actually tremendously difficult to handle. And there are some gaps that actually we identify that are preventing us from an easy access to deliverable, configurable, composable models that can be deployed directly without human intervention, so you can get the solutions despite all these decisions now that they have to be made traditionally by the user. So we notice that there is an ability to raise the semantic and syntactic dimensionality of mathematical models, and you'll see what I mean by this a little bit later. We also have a limited ability to convert mathematical models to computational models and derive and deploy their compositions with efficient resources. And we have also an inability to exploit existing numerical simulation resources. So we actually want to address the intersection of these types of issues and gaps. And to do that, we looked at the ladder of what really a model is in terms of the various spaces. So if the physical system can be considered a morphism of a p-dimensional input vector to a q-dimensional output vector, and you want to create an analytical model and then a computational model and then a visualization model, then you have the opportunity to either go from the analytical model to the computational model, but because there are codes out there that already have pre-encapsulated physics, you may also want to go backwards. That's the top-down and the bottom-up approaches. So we actually look at both of these cases. In the top-down approach, we actually developed 3 specific resources, all in Mathematica, which obviously now is playing the role of a meta-meta computing framework, since this is a meta-computing framework, where the first one develops continuous multiphysics equations that derived, that we really have to solve, that are actually defined in quantities over the field of reals. Then we have another one that does a hypercomplex semantic dimensionality raising that maps those equations from the reals to hypercomplex algebras like complex numbers and quaternions. And then we have another one that we call E to G, from equations to graphs, that basically raises the syntactic dimensionality from 1D forms to 3D or 2D algebraic solution graphs. Again, also defined over the complex or quaternion spaces. And on the bottom-up side, we have 2 additional resources that we created that you'll see as I go through. I don't want to spend more time on this. So what is the top-down overview approach here? On the bottom right here, you see that somehow we get some PDEs and we have to solve them by discretizing them. And FEA is one of the methods of doing this, among many others. Clearly, this is what traditionally has been done with what's been called numerical computing. But how do you get these equations? So for every system, you need to start from left side, where you have to decide what really your systemic behavior state variables are going to be, what are going to be the inputs and the output of the system, in other words. You have to involve conservation laws that you think they are holding. You have to establish constitutive relations to make those conservation laws algebraically closed, because you don't have enough equations for solving for all the state variables. You need to add in formulation axioms that perhaps simplify your life or serve as constraints to derive the governing partial differential equations with quantities defined in R, in the field of reals. Now, the next 2 boxes are boxes that usually have not been dealt with adequately in the history of development of models. And we are adding them here. But traditionally, you would go from the derived governing equations to the solving those equations. Now, we intersected these two modules because we wanted to show the effects of raising the semantic dimensionality and the syntactic dimensionality such that we can do that. And based on what I told you before, really the CMEB package creates the equations on reals. The R2H, R2 hypercomplex, in other words, converts them, raises the dimensionality semantically, and instead of talking with quantities on reals, you deal with quantities on complex or quaternions that are both hypercomplex algebras. And you finally use the E2G rewriter to raise the syntactic dimensionality in a place where solving is actually equivalent to path following. And I'm going to basically go and show you the first incarnation. Everything is being done in Mathematica, where we use really the user interface capability of the code that allows a user to define the state variables, to define what thermodynamic potential is going to be used in the derivation, which depends, of course, on the selection of the state variables, how many physics are going to involve, whether there are any material symmetries, whether there is an order of the constitutive laws that you want to deal, linear, nonlinear, up to what extent, and also the spatial dimension of the problem. And do it in such a way that the constitutive formulation axioms are all determined, are all observed, and at the same time we have control over them. So, for instance, for the principle of determinism, as you can see here on the right, all the dependent variables are depending on all the independent variables, depending on the problem you have to solve. So, with this type of mechanism, you can actually generate up to, if you consider that only one species diffuses into the material, you can develop over 1,100 theories or models. And on the left side, you see that this number can get very quickly very high, depending on how many species are actually incoming into the material and when they're interacting with this case. So this is an example of applying it to derive something that we have actually derived manually, and you can find references out there that we confirm, verify that indeed it produces the correct results for hydrothermoelasticity, actually anisotropic hydrothermoelasticity for one species. So it uses the Helmholtz free energy, creates the three types of constitutive equations for stress, entropy, and chemical potential, derives the algebraically open system, and then by plugging the constitutive equations into them, you get the algebraically closed system now that is solvable by various techniques if you decide to stay on the field of reals for all the quantities that participate in here. Another version of that is adding electricity to that. You have the anisotropic hydrothermoelectroelasticity. So now you end up with a similar process and the proper choices on the interface of 4 strongly coupled PDEs that one has to solve. So now we're going to the second package, which is the R2HC, the reals to the hypercomplex number, that essentially also has a user interface. And to give you an idea how it really works and what is the value of it, you see here the formulation of the elasticity problem in 2D, and on the right, the anisotropic elasticity also in 2D. And through the Airy rewrite, you can convert those PDEs into a biharmonic equation for the Airy stress function, that where the second derivatives give you really the components of the stress tensor. However, after that, if you use the Kolosov-Muskhelishvili rewrite to go from the reals to the complex numbers and introduce rewrite U now to be a complex potential for the isotropic case on the left and for the anisotropic case for the right, you end up with a system of algebraic equations, not PDEs, that you actually have to evaluate and not to solve. assuming that you can find the right potentials, which are these functions gamma, psi, and phi here, as you can see it, which particular for certain problems can be very quickly implemented, as you can see on the bottom. And an example, for instance, for a case of a medium with a crack that is inclined relatively to biaxial load, this corresponds to a Riemann-Hilbert arc problem that actually can be implemented by this method and give you direct evaluation of the solutions by essentially evaluating those algebraic equations. No PDE solving, so the dimensionality raising helped us not having to solve PDEs in this case. A 3D case, and the 3D case, as you can imagine, because the basis of quaternions is 4-dimensional and the Euclidean space is 3-dimensional plus time, you can actually use a quaternion isomorphism with the space, the Euclidean space, to essentially achieve the same amount. Go from the generalized momentum equation with a constitutive response and the kinematic relationship with temperature and end up with a set of algebraic equations. Now it's 9 that you really have to solve, but they are expressed in terms of 3-quaternionic potentials that you need to determine in a way similar to the one that you saw for complex numbers. Again, no need for discretization. The third resource that I wanted to talk to you about is really the E2G, the syntactic dimensionality raising tool that we created. So to give you an idea of what this actually does, let's take a subset of equations dealing with the dissimilar anisotropic elastic bodies in contact with 2 cracks that you see on the lower left here. And basically what this does, converts it to a 2D or a 3-dimensional graph that you see in the middle, that essentially, if you want to go from the node T, which are the stresses, to the node D, which are actually the displacements, all you really have to do is to find the path, one path that does this, connects those nodes, and apply the label of the edge on the label of the origin to get the label of the target. And the continuous arrows are actually tensor multiplication, and the dotted arrows are tensor addition. So this allows us now to take this full problem and formulate everything that can ever be said about what needs to be done for solving this problem. All quantities are now available, and solution here is equivalent to path following. The next thing is that obviously you can look at subgraphs of this entire construct, like the boundary displacement vector subgraph, the differential constraint subgraph, and the boundary stress vector subgraph, and so forth. So another resource that we developed is the bottom-up. In the bottom-up approach, now we're going on the other side, is the algebraic expression tree optimization system or metacomputing resource that was extremely useful for the large FEA codes that we have to use. Here you see what Mathematica gives you if you want to solve a quartic equation. And if you plot the tree of the solutions, you see that the leaf count is close to 3,000. So this resource, actually what it does is does a common sub-expression elimination combined with constant folding and propagation and global value numbering that essentially reduces the problem on the left to the problem on the right with an effective leaf count of 300 that makes the computation within a larger code extremely more efficient, especially when you need to compute Jacobians with very complex expressions that are involved into the constitutive equation representation inside the big finite element codes. Last but not least, in the bottom-up approach is the metacomputing capability that actually allows us to specify the physics problem specifying a numerical problem, specify the software problem, and specify the hardware problem. The last three, you do it only once. The first one, you do it every time you have a new physics problem, assuming that the other ones do not change. On the top, from the user's perspective, you have a graphical user interface to actually capture all these things and you save the results. But all these specifications actually need a machinery to compose them together such that when you push the button, they derive what you need to have a directly computable multiphysics models that involves legacy codes that have already pre-encapsulated physics. And you don't want to have to deal with the details of the input files or the glue files that allow us to move data from one component to another. So what we use here, we use categorical category theories abstractions like co-limit and limit, because as computer scientists have found out, you can, some of these operators, like for instance, the co-limit, allows you to perform specification integration. And that essentially is a tool for performing composition. So you can actually compute things that are missing by taking things that you have and performing co-limit operations on those. But what I'm talking about, these things are actually these specifications I mentioned before. So what we did, we created a 4-layer network where the top 2 layers are actually on metacomputing space. The bottom 2 are in computing and one lives in between, where the user can actually go and define a workflow of the physics that are needed just by essentially right-clicking and selecting the physics from your potential options that pop up and making the right connections to the ports. And this resource at the end creates, as you can see on the right, all the necessary files. Here is an input and a script file that actually the legacy code needs to run together with a script that actually invokes it. So in the bottom layer, we have the legacy codes that actually are going to be finally executed. And all the red things that you're seeing here are actually the parts of the input file and the scripts that you actually need to connect everything together. And to see how this actually works, you right-click, you select, for instance, a heat transfer problem. You know that to have a heat transfer problem, you need to have a medium with a geometry, and the geometry really needs to have material properties associated with it. And to make the very, I want you to see as you build things, there are things appearing on the right side here, which is actually those things that the legacy code needs in order to actually run after the entire process has finished. And since this is a particular NASA challenge problem that is a conjugate heat transfer problem, we have to involve not only heat transfer, but also fluid dynamics and solid mechanics. And essentially, once we finish with a heat transfer, we select the proper fluid dynamics node that requires also its own specification, and you keep following this, but as this continues, I'm sorry, it went. I have to go there. So as this continues, you have to realize that the two need to exchange. The heat fluxes have to really be aware, come from the fluid, and the fluid conditions have to go into the heat conditions have to go into the fluid, and so forth. So as you make these connections, code appears magically on the right that actually verifiably correct, that can now run and give you the solutions that you want. So we actually apply this on this air braking application that NASA had experimental data, several weeks to formulate, to find the right combination of choices for the input file and the scripts that are used to run this. You basically get immediately the file and you run it. So it's a multiple orders of magnitude differential in terms of throughput performance. And with that, I'd like to thank you and say that please feel free to send me any questions that you want on my email. I know that this is completely different than most of the talks that are slotted for this webinar, but I'll be very happy to answer to you.
So yeah, without further ado, I'm going to get started. So I'm actually presenting on two-phase flow with Mathematica, and what's quite nice about this is that we use Mathematica entirely to go from analytical, the analysis of the analytical structure all the way to a numerical solution. I would definitely have to say that the previous talk was quite a huge one to follow up. I think there was an amazing presentation and such a dynamic and different way of using Mathematica to do things. I suppose in many ways this will be very much a traditional way in which things are done. So I certainly hope everyone can see the slides in totality, and with that I will begin. So I mean, briefly put, two-phase flow is often modeled in one of two ways. Sometimes the model approach proceeds by combining these two different phases and creating a set of variables in which some kind of mixture is invented. Of course, this is a mathematical abstraction and doesn't represent anything physically real, but this approach has been well investigated and explains quite a few things. The other approach, of course, is to keep the phases separate and then model each of the equations and capture some kind of interaction between the two. In this problem particularly, this is the approach we follow for the sake of comparing, at least arriving at a set of solutions first before we can run some kind of comparison between the two kinds of models. So this phase-separated approach is typically referred to as the Zora-Abgral method, or model or equations, and that's what we'll be looking at in this presentation. So the set of equations are quite simple. There are many different ways to write them, but in sort of a semi-conserved form, what you end up with is a system of equations that look like a set of hyperbolic conservation laws together with a source term. It could be argued in some ways that this is correct or incorrect, I suppose, depending on your philosophical outlook, in the sense that on the right-hand side you have terms, as written out here, you have terms that are related to the spatial derivatives of one of the variables. So just quickly from the top down, what you have is the portion of gas density, so that the alpha tells you what the volume void fraction is. And so again, the proportion of momentum density in the gas phase, and in the third position, you have the proportion of liquid phase density, and then liquid phase momentum density. And then, of course, the respective bits and pieces that come together to sort of connect the two. And really, from there, you kind of want to perform some kind of analysis on these equations and try and find out a bit about the dynamics from the perspective of hyperbolic conservation laws, but also from the perspective of the Riemann solution to these problems. Two of the quantities that appeared in that equation refer to the interface pressure and the interface velocity, and they're defined, as you can see over there. And I've referred to the set of equations as the semi-conserved form. I call them semi-conserved just because they hold the old traditional conserved quantities, the mass density and the momentum. What's worth noting here is that the equations of state that connect these two are isentropic equations of state. And so there's a very particular way in which these things are going to evolve. As we now sort of start interacting with pulling out the eigenstructure of the equations, it's very simple and very straightforward to use Mathematica to just extract what this coefficient is. And it's always a nice way of checking just any system of conservation laws, whether they have a conserved form or not, the usefulness of being able to pull out the coefficient matrices and analyze those matrices. Now, once we have that, we end up with this elegant looking set of eigenvalues and eigenvector matrices, or eigenvector matrix in this case. And we can see immediately that from the eigenvalues, we have pretty much what we would expect. We have information from the gas propagating to the left and propagating to the right in the second element. In the third element, the interface velocity, and then information propagating to the left and to the right in the liquid phase. But what is even more intriguing is the actual structure of the eigenvectors, because the first two and the last two are quite intuitive. You'd expect to see something like that, nothing special. But the funny part is that middle eigenvector is obviously the thing that's going to cause us quite a bit of trouble. But its structure tells us a lot about what is happening at the eigenvalue that is the interface velocity. I remind you here that the eigenvalue ui represents the interface velocity. Okay, so we can put those together, and we can form a wave structure that has a very simple structure. We have waves going to the left and waves going to the right in the gas and the liquid phase. And then we have this interface velocity wave, so this middle wave, where we hope to find if there's a discontinuity starting at some initial position, how that discontinuity then propagates throughout the field. And so in order for us to now understand this, the eigenvalues only tell us one part of it. We now need to try and figure out exactly what the nature of discontinuities and jump discontinuities look like. So in actuality, the one thing that you want to do is you want to rewrite this equation in a quasi-linear form, because if you go back to the original set of equations, you pick up quite immediately that this is not a conserved form of a hyperbolic conservation law. In fact, whether or not the conserved form even exists is a question unto itself. But fortunately, for the purpose of analysis, we actually turn to the generalized Riemannian invariance, and we don't need Rankine-Huguenot conditions to investigate this. And the reason for this comes from a very simple fact that because we're using an isentropic equation of state for the liquid and for the gas phase, it means that the generalized Riemannian invariants are perfectly good to use to investigate discontinuities across the various waveforms that we're seeing. And that was for us working on this particular problem was quite a useful thing, because to try and generate Rankine-Huguenot conditions when you don't have a conserved form, you have to then start breaking the laws of exactly what the Rankine-Huguenot conditions tell you in the first place. But to move to the quasi-linear form and to just rely on the generalized Riemannian invariance made things a lot easier in terms of actually creating conditions that relate one set of laws to the other. And what we find from that is that the outside waves, the outer waves, are related to shocks in the liquid phase. The inner two are shocks in the gas phase, and they actually don't affect each other at all. So in other words, a jump discontinuity in the liquid phase doesn't actually affect the gas, and a jump discontinuity in the gas phase doesn't affect the liquid. Just the way that the equations are structured, this isn't too unexpected. The middle wave, the interface velocity wave, obviously raises a couple of interesting questions, because what are these? How does one describe these waves? And so if we have a look at the eigenvectors, we actually find out a bit about what's happening with that middle wave. What this work required us to do was actually to calculate eigenvectors, not just in the primitive variables, but also in the set of, let's call them semi-conserved variables, because a lot of information came through when we looked at both of these sets of eigenvectors. When we have a look at the linearity or the non-linearity of the middle wave, it's actually easy, almost trivially calculated, that the middle wave is a contact discontinuity. But what makes this a bit nasty to try and work with, and we know that from an Euler problem, a contact discontinuity means that the velocity and the pressure in that middle region remains constant. But in this case, we have two densities and two velocities. And because the law is isentropic, where do we actually find that discontinuity? And it turns out that, or rather that continuity, it turns out that the continuity actually comes from the interface velocity and the interface pressure. Those two things remain continuous across that middle wave. Okay, so obviously now what we want to try and find out is what these starred regions are. So these two inner starred regions across the I'll call it the λ3 wave. And then how we find those solutions relative to these outer ones. And so the left-hand and the right-hand states are obviously given, and we want to try and relate these left-hand and right-hand states to whatever's going on in the middle here. What I will say is that the positioning, just in terms of where this UL and this UR sit, is quite incorrect in the sense that you see, just because of the wave speeds, that the liquid phase jumps first as a result of the shock, and then the gas phase starts. So this UL and this UR kind of speaks for each phase, but in sort of a unspoken manner, if I can phrase it that way. In total, what does it mean for us? It means that we have 8 quantities that we're trying to solve. The 8 quantities come specifically from the 4 densities and 4 velocities in this middle region over here. There are, in fact, 4 other quantities, and they're the shock speeds of each respective phase on either side. And those are relatively simple to calculate, provided you've calculated the first 8 terms. If you can calculate the density and the velocity of each phase in the star region, calculating the shock speed is quite an easy thing to do. It's relatively standard. Okay, so going from that point, you're able to sort of generate, I'm just going to go one step back here. You're able to sort of generate a system of 8 equations that you want to sort of systematically reduce. And the standard Euler problem, you end up with this nonlinear equation that explains to you what the interface pressure is, or rather the star region pressure. And once you have the star region pressure, you can calculate the other quantities. Unfortunately, in this 2-phase case, you don't have the luxury of that. And the best you can do is reduce the 4 equations down to 8 equations, and then find solutions to Z equations, and then systematically work your way outward. So I refer to these specifically as semi-analytical solutions simply because at the end, you end up with a system of nonlinear algebraic equations you still need to solve. And so traditionally, these things have been done using quasi-Newton methods and that kind of approach. But I've been using Mathematica to solve nonlinear systems of algebraic equations for a relatively long time. And they actually work really well for these kinds of problems, and solutions are relatively simple to produce and sort of straightforward to compute. And you can actually go back and verify, how accurately those solutions have been calculated. So it was really useful to be able to derive the set of equations that result from the Riemannian invariance, and then to arrive at a system of 4 equations and solve for these 4 equations using Mathematica without having to then rewrite a whole bunch of code to solve for this using some kind of iterative method like a quasi-Newton or whatever else you could use. Once we had these analytical solutions, it was now time to compare it to something numerical. And so in a lot of the literature, the Zoral-Abgal equations are approached by, as I mentioned before, splitting them into this conserved flux, this conservative flux, and then the source term. And I found that this approach made me a little bit uncomfortable because the source term introduces the need to balance and do all sorts of other weird things to try and make sure that the equations balance out. The eigenvalues produced what we would expect, so it would be more imperative or more sensible to write things as a quasi-linear equation, quasi-linear system of equations. And so that was the approach that I used here. And to this end, there was a couple of years back, many years back, in fact, a method by Chakravarti in which only a quasi-linear form was available. And so in quasi-linear form, you're able to then break up the equation using the standard splitting techniques of finding out which waves are going towards the left, which waves are going to the right, and then taking upward and downward calculations or derivatives in the spatial domain appropriately. So the general algorithm that I used for this is given in this system below, and over there you can see the splitting that takes place. So you have this A plus, which is in essence the coefficient matrix that only contains the rightward going waves, and the A minus containing all the ones only going leftward. So this first numerical simulation was chosen to be a piecewise constant method without anything fancy really. The idea was to start off small and try and calculate or try and run simulations that would allow us to see what the overall behavior was. Now, previous calculations had typically bombed out a lot sooner. Things like the Lax-Friedrichs method, Lax-Wendorf method, the TVD slick methods, those weren't quite working out until the splitting had come into play. But the nice thing about the algorithm as it's written out here is that they are naturally extendable to piecewise linear TVD extensions to whichever level you want. I will mention that one of the important facts is that increase in the resolution didn't actually fix or make the numerical results any better than what they were. But comparing the numerical results with the analytical ones, in other words, we're just looking at what values we found in the star region. And if the values in the star region are in agreement with each other, we can then easily just back propagate our solutions and come up with this idea of how accurate our numerical method is relative to the analytical one. And so what that did was allow us to compare the analytical solution with the numerical one, and everything looks relatively good for having this alpha that starts out initially. So the whole idea is that in the middle region you're going to have two differing values of alpha, and the test that is being run here is for the case of a force shock propagation. So both phases are sort of in a collisional initial velocity, and that generates force shock waves that propagate outward with some speed. The initial test that is currently in the literature is only the case where alpha is constant across the middle sort of interface. This is fine until you start decreasing the values of alpha, and there's now a jump on the left-hand side relative to the right-hand side, and that makes the calculation a little bit complicated. And so it was nice to arrive at a situation where we could actually look at analytical solutions for the case where there was a difference in alpha value in volume void fraction across the jump discontinuity. And the table kind of illustrates, and the results are relatively good when you compare the analytical to the numerical ones, except until you get to 0.1. Now in the 0.1 case, you have the left-hand side, which is mostly gas, and the right-hand side, which is mostly liquid. And so obviously you expect that this is sort of a highly nonlinear problem, and instability is expected. So we can see that there's a distinct divergence from the analytical solution when you look at the numerical one. And so obviously something weird was going on. And so when we had a look at the numerical method, we could see immediately that there was a certain level of instability that was going on here. And so there was a dip in the numerical solution first before the expansion took place. And this dip then propagated, almost pretending to be something completely physical, when the analytical solution tells us that that's not quite the case. So obviously there's a need to go and investigate that numerical method in some detail and try and extract, hopefully develop a numerical method that can handle the opening of that Riemann fan right at the beginning of the simulation. So to that end, for any value of alpha that's not too low, the numerical method and the analytical method actually agree relatively well, and that's a good sign. But as we get lower and lower, we want to actually change the numerical method that we're using to something more useful or more accurate. So potentially piecewise linear or piecewise parabolic, something that's going to be able to just capture the effect at the beginning in the simulation when you start that simulation. As I mentioned before, increasing the number of points. So in the simulation over here, this was done for about 1,500 points. I'd done simulations of this kind all the way up to, I think it was 25,000 points. And the numerical method just resolves this anomaly, and it just makes it a lot clearer, which is obviously not desirable. So we know that that's producing something that it shouldn't. And so we have to now turn towards better numerical methods to try and fix that issue up. And that's it. There's a couple of references, and yeah, thank you for listening. And again, thank you to the organizers of the colloquium.
Hello, everyone. Yeah. So first, many thanks for giving me this opportunity to just present our recent work. So today I'm going to talk about this simulation of friction between atomic layers by using a 2Q model. So if you want to know more about this work, you can check out our publication in 2022 in this Tribology International Journal. So this work basically was done at UCL when I was at this Institute for Material Discovery. We basically studied the frictions between atomic layers by using this basically Newton equation, PDE. Yeah. So first I will give a brief introduction about the background of our work, and then I will talk about the computation method, and also I will present the results. Finally, I will give some general conclusion. So basically, what we are simulating in this scenario, just you have some two-dimensional sheets. Yeah, you can imagine something like a graphing sheet, and you also have a substrate underneath this sheet, and you use this so-called atomic force microscopy tape to study the surface, to study the sheet, essentially. In this setup, so what you can see is the response of this tape, just when this tape interacts with the sheet and also the substrate, actually. So this is the I think this is a very effective method to study friction and also the relative motion between the sheet and the substrate. So the further background is friction is a very important for daily life. I think studying friction, especially between atomic layers, is very worthwhile. So the for this work, we just studied friction from a microscopy perspective. So previously, just this kind of problem, okay, has been studied by using so-called this 1Q model. So basically, the you have well, the 1Q model. The essence of this 1Q model is that you describe the motion or the deformation, essentially deformation of the sheet by using a Q parameter. Okay, there's a Q parameter. Yeah, but you just you just forget about the detail of the substrate. Yeah, our work just take this back, take into account this the motion or deformation of the sheet, which is I think in reality you indeed have the deformation or the motion of the substrate as well. Actually, our work compared with the previous work in this Nature Communication paper is that we take back this motion of the sheets, okay, to get coupled, and the motion, okay, of the substrate will be coupled with this motion of the sheets, okay, by introducing another Q parameter. Okay, now we have 2Q model. This is why we name this model as 2Q model. 1Q, this Q1 is for the sheet, and this QS is for the motion or deformation of the subject. Okay, yeah. So if we have this picture, okay, then it's clear that we can use this Newton's second law of motion, finite element method, okay, essentially to solve this 2Q model. Okay, yeah, we have essentially we have the potential of the sheet and the potential of the substrate, okay, dependent on Q1 and QS respectively, and then we have this interaction between the tape and the sheet, and the interaction between tape and the substrate. Then we can build up this potential, okay, and once we have the potential, we insert this potential into the PDE. Then we use this Mathematica 13, okay, this software to solve this three, okay, together, these three partial differential equation. Okay, yeah. So I think the most important part of this part is the potential between the there's another part of this the potential between the sheet and the substrate. I think that just these three potential are very important description of this relative motion between the sheets. Okay, yeah, but these three potential, okay, should be computable by using the other first principle method like tangent function theory or force field. Okay, so yeah, this is another open question. Yeah. So basically, our procedure is a first way benchmark the single Q model in this paper. Okay, that is successful, and then we design the appropriate potentials. Like I said, these potentials. Okay, to describe the interaction between the films and the substrate, and also between the film and the AFM tapes. Okay, and then we have this 2Q model, and we solve this 2Q model. Okay, and this is the parameters we use in Mathematica, and then this is the equation. We have this function, and we can insert these parameters. The parameter for the potential, and also this parameter B and C are the lattice contents for the sheet and for the substrates. Okay, and then we solve this partial differential equation in Mathematica. So this is straightforward, and also we can just we can compute the time evolution dependent on the different potential parameters. Okay, this 2D 3D plot. Yeah. So and these are the results, and we just the right curve is for the sheet, and the green curve is for the substrate. We can see the different they have different motions sometimes, and we can compute the difference between these guys are difference between these motions between sheets and substrate. Okay, yeah. Yeah, that's we can see some interesting behavior. Okay, for example, these guys, okay, it's quite regular. Okay, they just have a coherent motion between the sheet and substrate. But for this one, okay, you can see the motion. Okay, they split. Okay, that is not a stable configuration for that kind of potential. Okay, these relative motion are highly dependent on these potential parameters. But we have so many parameters, so we can just we cannot sample this one by one. And the whole paper is just it's quite about this methodology. Okay, yeah. Later on we can talk about it, and then we just in this step we just fix the time. Okay, essentially we have the time evolution here. Here we just fix time. Then we just plot this relative motion. Okay, depending on the parameters. Okay, potential parameters. So the reason why I said this paper is about methods. Okay, we just introduce this. We just introduce another Q. Okay, for this multi-layer structure. This two-layer structure essentially. Okay, but you can imagine if you have in reality. Okay, for devices you have multi-layer. Okay, 4 or 5 layers. Okay, essentially you grow these layers one by one, right? If you know this material fabrication, okay, then you can use this method, okay, by introducing different Q for different sheets. Then you can work out the relative motion between these sheets. Okay, this is essentially for the variable technology. When you have multi layers, okay, then you can use this method to analyze the relative motion or the stability. Okay, how stable these structures. Okay, you can use this kind of method to analyze the device structure stability. Yeah, I think that's it for my presentation. Yeah, thank you for listening. For listening. Yeah, thank you.
Good morning, good evening, or good afternoon. My name is Huilong Ren, and I come from Leibniz University in Germany. And this topic is about the non-local operator method. an integral approach for solving partial differential equations. And my presentation contains the following 4 parts. Firstly, I will talk about the motivation, and then I will show a typical example of the non-local model. In the third part, I will talk about the non-local Pareto method as a generalization of the dual horizon dynamics. At last, I will show you a list of examples. So, about motivation. Why partial differential equations? Because partial differential equations are the most complex mathematical language for physical models. The physical model can be very complicated, and it can have different form, but the mechanism behind it can be very concise, very simple. So if we can conquer the partial differential equation, at least solve them, then we can solve most of the physical problem. There are many different partial differential equations, such as the harmonic equation, the von Karman equation, or the phase field equation, the Kahina equation, or the Navier-Stokes equation. And so if we can solve the partial differential equation, we can solve most of the problem in physics, especially in the engineering field. So in the calculus talk about the differential and the integration. But PDE belong to the differential equation. The general form of PDEs is that its equation consists of derivatives of different orders. And these derivatives are defined at the point without signs. So it's a differential equation. In this sense, we say that the differential equation are local model. But on the contrary, there are many different other models. The integral. In the calculus, integral and the differential are both the integral and the differential are important. But in PDEs, there is no integral. And the integral has a size. It has size of the domain. And the non-local model is completely different from the differential equation. And in physics, or in the natural world, there are many examples, such as the universal gravitation, the quantum entanglement on the social network, or the contact model, or the paradigmics. And this model is completely different from the local model, because in this model, we cannot use the partial or the derivatives to describe the system, because it describes the interaction between 2 points. And in this system, there's no guarantee of continuity. And I think a non-local model offers a new insight to view the many physical phenomena. And now let's return to the partial differential equations. When we have the partial differential equations, want to solve it. Usually, we use the energy form or weak form to solve it. The PDEs for many physical problems can be formulated as energy form or equivalent weak form. Conceptually, they can be written as the energy functional integral of any density in the domain, and the energy density, the integration of energy density on different boundaries. And then we discretize this energy functional based on certain numerical schemes, such as finite elements method, or as geometric analysis or machinist method. We can describe or express the derivatives of unknown field with matrix form. And then, based on the variation principle and the vertical residue method, we calculate the first variation and the second variation of the energy functional to get the residual and the tangent stiffness matrix. When we have the residual and tangent stiffness matrix, we convert the partial differential equation into a set of algebraic equations. Now, I will talk about the typical example of non-local model, integral model. And the second part, I'll talk about the dual horizon paradigms. First, I want to review what is paradigmics. Paradigmics is a theory that describes the model contains both continual condition and the discontinuous condition. it can deal with discontinuity and continuous at the same manner. In the paradigmics, the most important concept is the horizon. What is horizon? Horizon is a neighborhood with finite size, and this finite size has any point for inside in this horizon can have interaction, and at any point in the horizon, we need to use the information in the nearby point to define the information as the point x. And so then we discretize this domain into sets of particles. Any two particles can interact with each other, and this interaction is direct direction. This is different from the local model differential equation. And there are several different paradigm formulations, such as the first is a bound burst. In the bound burst, any 2 points has an interaction. This interaction acts like a spring, and then it's the state-based paradigmics. And in the state-based paradigmics, it contain complex material constitution. And the one feature of paradigmics is that it uses integral equation, not differential equation. In elasticity, the elasticity always use the partial differential equations, but in paradigmics we always use the integral equation, because for many problems contains discontinuity. Partial differential equation has problems, has difficulties, but for the integral equation, we can modify the integral easily, so we can model the fraction very easily. So the fraction is a natural outcome of the simulation in the integral equation. And there's one big problem for the paradigmics. It requires that horizon or the neighborhood be constant for any point in the domain. So if we discretize the domain with different particle size, and the number of neighbors increase exponentially. But in finite elements method, we can use different size of mesh. So can we do that in paradigmics? Adjust the horizon based on the size of the particles. So my first discovery is I define the dual horizon, and then modify the paradigmics, the fundamental, and propose the dual horizon paradigmics. So with this new theory, I can describe the domain with an arbitrary refinement and arbitrary particle distribution. Now the set part about the non-local paradigm method. This non-local paradigm method is very simple, and we just use the non-locality to propose a general numerical method. And similar to the dual horizon paradigmics, use support and dual support, the neighborhood and the dual neighborhood. And we define the non-local gradients, non-local curve, and non-local divergence. With this definition, we use a pure integral to define the non-local operators. So with this operator, we can introduce a lot of non-local theory, such as non-local diffusion, non-local Maxwell equation, and the non-local phase field. And we also propose the high-order non-local operator method. And with just one simple expression, we use the pure integration. We can define the non-local derivative of different orders. So we can also, after discretization, we can actually, this method is very powerful because it's based on the variation principle and the verticality method. We can use it to solve the loss problem. And loss problem solved by FEM can always solved by this NOM. And in this, we can solve different problems, such as time dependent on the nonlinear problem or the high order partial differential equations. Especially we solve the 8th order partial differential equation for the 3rd order gradient elasticity. And how can we do that? Because I use Mathematica. I use Mathematica to generate the source code for NLM. And the Mathematica can do symbolic and algebraic calculation. It can also do the automatic differentiation and automatic code generation. And most importantly, you can generate the source code like C and Fortran. So the first example about the phase field reflection propagation. We use this only simple energy functional, and then we apply the boundary conditions. We can see the propagation of the crack go horizontally or on the top down side. And this is the nonlinear problem for common plate with large deformation. And we only need this energy functional, and then we solve it with the NLM and compare the result with abacus. On the left bottom, we can see it's agreed very well with the abacus. And this is the 2D electrostatic field problem. We only need this equation boundary condition, propose the equivalent energy functional. We solve this problem and compare with the analytic solution. And this Maxwell equation just formulates the energy functional, equivalent energy functional, and solve it. And we've solved the rectangular waveguide problem. And we compare the eigen frequency with the analytic solution. The first three modes. We also apply NLM to solve the flux electricity. Flux electricity is a generalization of the piezoelectricity. The energy function for this problem is something like this. And we solve a 2D tube with axial symmetric cross-section. We also compare the numerical solution with the exact solution. Agree very well. And we apply the NLM to solve the Cahn-Hinard equation. Cahn-Hinard equation is a high-order partial differential equations, but there's no problem for NLM. You can see several examples in 2D and 3D. You can see the concentration, the evolution concentration, and the influence of the internal boundary. And we also apply it to solve the metamaterials, the periodical structures. Metamaterials is very common in natural world. We also needed only the energy functional when we solve it. And this is the example of cube with the inclusion in 2D and 3D. We compare the dispersion scale with the finite element method and the in the commercial software. The dispersion scale agreed, they're very close. And we also calculate the more complicated problem. The gradient elasticity, the gradient elasticity metamaterials. And we also use to solve the gradient elasticity. This is a high order continuity. And we compare in 2D setting, we compare the result with the exact solution. This is a theory. Categorical theory is very complicated, but no problem for NLM. And this is an infinite plate with a hole. And the displacement contour of gradient elasticity for different length scale. Exact solution and the NLM. And I want to show also a fracture problem is dynamic rate of fractures. And this is an impact on 3D block, high velocity impact. And then you can see the propagation of the crack. And this is a snapshot of the crack. At last, I will show this is the Kassoff-Winkler experiment in 2D. Also impact on top. And then you can see the crack propagation horizontally. So this is my presentation. I want to show that FEM is very powerful, just like FEM, so not a problem. Thank you for your attention. Yeah.
Thank you so much. So I'm going to talk about our recent works in the realm of quantum mechanics, more specifically in the quantum trajectories formalism associated to quantum mechanics. I'm Mateus. I'm going to present the one-dimensional solution of the quantum trajectories in one-dimensional systems, while Henrique is going to present the two-dimensional quantum system that presents chaotic behavior. So basically, quantum mechanics is the fundamental theory used to explain the behavior of matter and energy in both atomic and subatomic scales. And is usually described by the wave function psi, which evolves accordingly to a Schrödinger equation, which is a partial differential equation that depends on both the spatial and time. And this equation is different from system to system, where the difference lies in the presence of this potential V here. Each system has a different potential, and as more complicated the potentials, we have more complicated the Schrödinger equations. And M is the mass, and H bar here is the reduced the Planck's constant, which is the Planck's constant being a fundamental constant related to quantum mechanics. So basically, I think that it's well known that quantum physics fundamentally diverges from classical physics, because while classical mechanics has a deterministic evolution with well-defined positions and a continuous energy spectrum, in quantum mechanics, on the other hand, we have description given in terms of the Schrödinger equation, and we not have a deterministic evolution, but we have a probabilistic nature given in terms of psi square. And this implies a quantized energy level. So it's two completely different descriptions of the nature in different scales, classical scales and quantum scales. However, exists one particular approach, the quantum formalism approach, also known as Bohmian mechanics, that can serve as a bridge between these two realms, the quantum mechanics and classical mechanics, because it introduces the quantum trajectories while it presents a non-local quantum potential. So for us understand that, like once the wave function is a complex function, we can write it in the polar form and insert it into the Schrödinger equation. Once we do that, we gain two equations. The first equation is a continuity equation, very similar to hydrodynamic equations. So we can include Bohmian mechanics to study the hydrodynamic formulation of quantum mechanics. And the second equation is a well-known equation in classical mechanics called the Hamilton-Jacobi equation. The only difference between this quantum version of the Hamilton-Jacobi equation is exactly the presence of my quantum potential Q that depends on the reduced the Planck's constant, and because of that, we call it the quantum potential. So that in the limit, when the quantum potential goes to zero, we recover the quantum description recovers the classical mechanics. So it's a very good manner to study the quantum to classical transitions of systems. But for we can interpret the quantum mechanics in the light of the classical physics, we need to assume that the gradient of S is the phase of the wave function. We assume that the gradient of S is a momentum in such manner that this term here, P squared over 2m, is a kinetic energy. And this Hamilton-Jacobi equation can be seen in some sense as an energy equation, where we have the energy potential, the classical energy potential V, and we have the quantum energy potential Q. So once that we assume this guidance equation, the momentum is equal to the gradient of the phase. If I took a unitary mass, this equation can be seen as a velocity field equation, such that if I integrate my velocity field, I can obtain the trajectory of the quantum particles in function of time. So this is a different manner to understand quantum mechanics, but that have the same results of the usual manner, the usual probabilistic manner to understand quantum mechanics, but has some advantages. First, it's a trajectories-based theory with a classical analog, and allows the study of quantum to classical transition in a extremely more clear manner than the usual manner. And because of the similarity with the classical mechanics, we can study complex subjects like the case of the quantum chaos, as going to be seen, it's going to be showed by Henrique, in a very similar manner than classical physics. But the main question is how to obtain the quantum trajectories. And that's precisely here that we use the Wolfram technologies in our favors. Because usually what is done in the study of the quantum trajectories is consider systems, quantum systems that we have a very well analytical, we have analytical solution of the Schrödinger equation. But is in some sense complicated to find such systems because it's a very simple systems that usually do not serve for practical for practical applications. So we use the Wolfram technologies to make a full numerical approach of the quantum trajectories formalism, because we start by numerically solving the Schrödinger equation for a given initial wave function. The second step, we obtain the phase S and compute the associated velocity field. And once we have the guidance equation, we integrated this equation in time to obtain the position of the quantum particles. So the details can be seen in this article here. I can put later on the chat the link for our article. And basically what we do in this article is consider a quantum harmonic oscillator, but with a time-dependent external force acting on it in such manner that we usually don't have analytical solutions for this this one-dimensional Schrödinger equation. So to solve the Schrödinger equation, we consider a Cartesian decomposition, and we insert this form here in the Schrödinger equation, and we gain a set of coupled partial differential equations. We consider initial conditions, combinations of the eigenstates of the wave function, and boundary. We assume that the wave function is zero in the boundary. So in order to solve these two equations here, we declare two operators, one for each equation, and we notice that the best method that preserves the wave function normalization is the method of lines, where we use as a spatial discretization technique the tensor product grid. And once we define this function here, we just use the n-dissolve function in Mathematica to obtain the solution of the Schrödinger equation. And to do that, we declare the operators as zero, and we give the boundary conditions. And we use the method that we define here. So we obtain the evolution of our wave function. So once we have the wave function, we need to obtain its polar form because we compute the solution in the Cartesian form. So we need to convert from Cartesian to polar form. Which can be done by the high school algebra, basically. So once we obtain the radial part in the phase of the wave function, we can compute the derivative of the phase in order to the spatial position, which is done by the derivative operator in Mathematica. And once we do that, we have the velocity field of our system given by this guidance equation. So we integrate the guidance equation over time to obtain the quantum trajectories. It's done quite simple by the n-dissolve function, where we use as a method the explicit Range-Kutta with difference order h and fixed time steps. So for a given initial condition, here I consider x0 is equal to 0.2, I just need to give to the function that we defined here the initial condition, and we obtain the associated quantum trajectory. So we do this for a lot of trajectories. This case here is just to show the robustness of our numerical procedure. We consider the external force being zero so that we can have just a quantum harmonic oscillator, which is very known system in quantum mechanics literature because it has an analytical solution. And we show we show our the validity of our method of numerical procedure by considering the Ehrenfest theorem that basically says that in average, the average of our system behaves as a classical system. So we consider a different, each line here is a different quantum trajectory for a given a different initial condition. And as we integrate the guidance equation, we obtain these quantum trajectories here. When we compute the average of the quantum trajectories, we obtain a classical behavior. That's just the classical equation of the harmonic oscillator. Each point here represents our numerical solution that comes from the obtaining the quantum trajectories, and the lines represent the classical solution. So we can observe a perfect fit between the numerical solutions and the classical solutions of the harmonic oscillator. So, but we consider also more complicated systems. We consider, for example, a Gaussian force. Is like an impulsive force that acts just for a short period of time. Despite looks like to be a simple case, it's a complicated to solve analytically. We don't know how to solve it analytically, but we find a numerical solution which also, again, in average, reproduce the classical solution that we are expecting in our case. So this is a very powerful method. Also, we have observed for a sinusoidal impulse, we have observed a quantum resonance within the quantum trajectories, which is we are not expecting that, and it's a very, very beautiful result. We also consider a more complicated case, the Duffin oscillator case, where we consider, besides the harmonic potential and the external force, which is sinusoidal, we consider a quartic interaction. So in this sense, the quartic interaction we do not have a Ehrenfest theorem for quartic interactions, but if we treat this interaction as a perturbation, we can show that we have approximately that the Bohmian average approximately obeys a classical solution. So this is a very important case because the Duffin oscillator have a lot of applications in chaotic dynamics, in physics, in engineering, electrical signals, biological systems. So if we have a precise solution of the Duffin oscillator using the Wolfram technologies, we pave the way for a lot of studies concerning this helm. So here I have the two references, our article and our program is always in Wolfram community. I'm going to pass the word now for my colleague Henrique. It's going to talk about the quantum chaos.
Okay, I need to clarify that I need to skip some slides. So the definition of chaos in classical mechanics is that a small change in the initial conditions corresponds to a very different result in the trajectories. So how to treat a quantum system in a chaotic perspective? A way to do that is by Bohmian perspective. We define for classical systems the Lyapunov exponent, which is here in this equation for lambda, and the equation for the deviation of its trajectories. In some systems, we didn't have the deviation of the momentum, only the coordinates. But in Hamilton equations, we have the coordinates and momentum. So the deviation of the trajectories are calculated by this formula, and the Lyapunov exponent is by the formula in the left. The characteristics of chaos are the unpredictability. So we don't know how the trajectories behave after a small change in the initial conditions. A periodic behavior. The main characteristic of the system is the sensitivity to initial condition. It appears in nonlinear dynamics. It's not sufficient for chaos, but all chaotic systems are nonlinear. It's present. It exhibits exponential deviation of neighboring trajectories. And in the case of a strong case, which we treat here, they present a positive Lyapunov exponent. It's not a case of the weak case. In the weak case, the Lyapunov exponent is 0, but it presents a small deviation in the trajectories. The existence of quantum trajectories enables the study of quantum chaos from a classical point of view. So we treat in the same way of we treat classical systems. So it's a definition, as Mateus previously mentioned, the continuity equation. If R square is equal to a density in a fluid, it corresponds to the same equation of in hydrodynamics. And here, the Hamilton-Jacob equation, like with an effective potential, namely quantum potential, as Mateus mentioned. The guidance equation is solved by defining the momentum as the gradient of S, which is equivalent to the equation below in terms of the wave function. The imaginary part of the gradient of the wave function over the wave function. So we simulate with this equation, not the equations previously mentioned. The Hamiltonian of this equation is given by a equation, a two-dimensional equation with x and y, and the coupling of the off diagonal coupling harmonic with x and y too, with kappa being a constant coupling. If kappa is 0, we can separate the system in two independent systems in x and y. But if we couple the system in the simple way, we have a system which cannot be uncoupled in a trivial manner, because we have a quartic and a cubic interaction. So the Schrödinger equation for the system, taking account that the px and py are operators, we have an equation of this form below, a Schrödinger equation. And we use a symmetric initial condition with a state 0, 0, 0, 1, 1, 0, and 1, 1. And in this figure, we show a solution for t equals 0. Abstract code is provided here, and we need to emphasize that in a couple of days we are sending this the full code for the Wolfram community, and we define first the derivative in x for the wave function after the solution with the finite element methods, which it's now a native function of Mathematica, and it's a great thing. And secondly, we calculate the derivative for the y coordinate, and after that we calculate the gradients with x and y, and second derivatives only for illustration. After that, we solve with the interpolated function a set of guidance equations with conditions x and x plus epsilon, where epsilon is about 10 to the power minus 5. We use end-the-solve value, which gives to us interpolated function x and y, and after that we perform the Lyapunov exponent for the pair of initial conditions. Here we use 6th pair of initial conditions. After that, we perform the average of the Lyapunov exponent and store the data to don't forget the results. So here are the first results with y versus x. So we use symmetric initial conditions in sense of x and yx, for instance. So we can see that the solution is indeed symmetric, and it's a good way to test our results if it's good or not. So all solutions for kappa equal 1 equals to 0.5, 0.05, and 0 are symmetric. So, but in the case of kappa equals to 0, we have a well-behaved function. So it indicates a presence of an ordered state. So it's not chaotic, but in the case of kappa equal 1 and kappa 0.5 and kappa equals 0.05, it presents some kind of chaotic behavior. It can indicate that in the case kappa equals 0.05, weakly chaos, for instance. But in the case kappa equal 1 and kappa 0.5, it corresponds to strong chaotic behavior. So here an illustration of this deviation, proving that the trajectories are indeed chaotic, strongly chaotic. We use conditions about 10 to the power minus 4 in the initial conditions, and even so, the trajectories deviate the behavior. So here are the results for the average of the log of the deviation for 8 bar set as unity. We have for kappa equal 1 increase, in fact, an increase of the Lyapunov exponent, indicating an increase in the Lyapunov exponent. So it indicates the presence of a strong chaos. In the case of 0.5, it corresponds also a strong chaos. In the case of kappa equals 0.05, it indicates that the Lyapunov exponent increase, but in some time, about 150, the Lyapunov is the Lyapunov exponent is 0 because it's constant. Here it's not the Lyapunov exponent; it's the mean of the log of epsilon of psi. In the other case, we vary the values of 8 bar. We use 8 equals unity, 8 equals 0.5, 0.05, and kappa maintain it as the unity, and it indicates invariance in terms of the H bar. So for H bar approaching to 0, it's the classical it's the classical analog because it's the equivalence principle. So varying H bar doesn't change the way that the chaos appear. So it's a great result. It indicates that we can treat quantum chaos in the same way of the classical chaos, and we can set, for instance, 8 by equal 1, and the Lyapunov exponent can be the same. Or the same of the result for H bar equals 0.5, 0.2, etc., and so forth. So I finish my presentation here. Thank you for the inviters and all people that are watching me, and thank you.
Hi everyone, I'm Chen Wang. I'm glad to be here to share my research about a new approach for simulating aquifer test. Aquifer test is a way to know how water flows and the behaviors under the ground. Traditional method has some problems, such as parameter correlation and high computational cost. Now, I propose a new approach to avoid these problems. Let me introduce more details in my presentation. There are 3 parts in my presentation. First of all, we have to learn about slot test and transfer test. They are both types of aquifer test and are used to estimate hydraulic parameters. Slot test is immediately remove the water in the testing well and then measure the recovery of the water level. Then we can get a curve about the temporal drawdown distribution. As for transfer test, it's injected into a transfer is injected into a testing well, and the data of concentration are measured in the nearby observation wells, just like this. On the other hand, wheel drilling may produce skin around the testing wheel. The skin has totally different hydraulic properties from the surrounding aquifer, which means a two-zone system, as you can see in this figure. This is the skin, and this is the aquifer. Now, the question is how to consider the skin in our model. Traditional model has two problems. The first one is parameter correlation. As mentioned earlier, we get the data from field test. Then we adjust the value of parameters to make the model prediction closely match to the data. However, in the traditional model, correlated parameters produce the same effect. For example, when the parameter A is 1 and B is 2, the model prediction can agree well with the data. If there is parameter correlation between A and B, we can also achieve a good agreement for A is 2 and B is 3, or A is 3 and B is 1, or even more combinations. Finally, we find that as long as the value of A and B fell in a range, the model prediction can all agree with the data. In other words, there are multiple optimal parameters. If there is no parameter correlation in this model, for A is 2 and B is 2, resulting a good agreement with the data. It's the only one result for A and B, means the optimal parameter. But for traditional model, here we can see that the traditional model will be 3 or even more results. The other problem is the high computational cost. As skin width is so small, it requires fine skin discretization, as you can see in this figure. That means high computational cost include slowing computing and much memory. On the other hand, due to the huge difference in size between the skin and the aquifer, it will be difficult to develop the grids. To solve these two problems, I modified the traditional model. This table shows the new finding of my research. Traditional model consider the skin as with governing equation. This is well known in textbooks and other papers. For the modified model, the skin is considered as a boundary condition. I inserted a new term into the boundary condition, introduced the skin factor into flow model, and the lagging time into the transport model. Pay attention that I derived the analytical expressions for skin factor and the lagging time, so they are not empirical parameters. However, I found another issue while using Wolfram Mathematica to solve this numerical model. The Newman value of mathematical function ND-solve is used to deal with the new boundary condition mentioned above. But it can't include a differential term to time. So I have to ignore the new term, this new term. This result in the numerical solution of the modified model being unable to solve the problem of parameter correlation. So there is a suggestion for Wolfram Mathematica group. Maybe you can consider the Newman value of ND solve function can include a differential term to time. Okay, let's move on. The results. Transfer tests being conducted in the laboratory. This is the standbook representing an aquifer. The skin width is 5 centimeters. This figure shows the best fitting curves of modified and traditional models to the data. The horizontal axis represents time, and the vertical axis represents concentration. We find that both the two models can agree well with the data. But the skin for modified model is 4.8 centimeter. It's very close to the real skin width. However, for traditional model, because of parameter correlation, the skin width is a range from 1 to 14 centimeter. We can't get the reliable parameters. There is the same result in slot test. Although both the two models can agree well with the field data for slug view and observation view, the modified model has only one optimal parameter estimate. The skin width is 3.4 centimeter, but traditional model has a wide range of parameter estimates. The skin width ranging from 1 to 6 centimeter allows the model prediction to agree with the data. Let's talk about the computational efficiency. Here is a parameter called AI, accuracy indicator, when the value of AI is unity. The volumetric of water keep balanced. The efficiency indicator is computing time ratio. As you can see in this figure, for modified model, the number of nodal points is only about 1,400. The AI approaches unity, but for traditional model, due to the fine skin discretization, it requires 206,000, and the computing time of the traditional model is 600 times that of modified model. For slot test, the modified model only needs 1,300 nodal points, but the traditional model requires 30,000, and the computing time of traditional model is 200 times that of modified model. That indicates the modified model significantly enhances computational efficiency. Here are our conclusions. First, we modify the models for slug and transfer test. The new model can agree well with the field data. The analytical solution of the modified model has no parameter correlation, and the numerical solution of the modified model has low computational cost. Finally, we have a suggestion for Wolfram Mathematica group. The Newman value of ND solve function can include a differential term to time. That's all. Thank you for listening.
All right. Thanks very much, everyone. It's been a real pleasure being here for this event. Thanks once again to all of our fantastic presenters. And we hope to see you next time for similar events. Be sure to check out the Wolfram calendar for more great Wolfram U events. And we'll look forward to seeing everyone next time.